So, all right. So, what we want to do today is just introduce you to some of the ideas that CPEP, the Contemporary Physics Education Project, has for teaching plasma and fusion topics in the classroom. And in case you are not aware, Contemporary Physics Education Project is a nonprofit group that is attempting to get ideas in modern physics out to high school and college classrooms. And Katrina Brown is one of the presenters today, and I'm one of the presenters today. And Peggy is also a member of CPEP. So she's here to help us out, I think, when we are got any questions. And some of the workshop highlights that we're going to go through are our CPEP YouTube videos, classroom-ready resources such as simulating fusion, plasma globes, and capacitance. And there we go. And the physics of plasma globes. And we hope to get some discussion from everybody who's here. And the first thing that we'd like to do is show you a little bit about our website and see if we can go back to our website. Is just cpepphysics.org. And the things that we're going to be talking about today are all available to you on this website for free. If you want to purchase the charts, you can through Amazon. But if you look here, for example, if we go to plasma physics and fusion, the chart is there. You can take a closer look at the chart and project it if you want to, the different parts of the chart and so on. So we'll be talking about that today, as well as going to...
So the charts were what CPEP started out making to present in a succinct manner the most up-to-date research and knowledge on these topics that weren't typically covered in high school and college classes. So we still do the charts and we still keep them updated. So particle physics, there's the nuclear and fusion, which we're talking about today. Gravitation has just joined us, and quantum has as well.
All right, and I will jump back to the PowerPoint on that one because we have the different charts here. And CPEP started out with the fundamental particles and interactions, built onto that with nuclear science. And the third chart was actually fusion. Katrina and I chose to start today with the fusion chart and have the first workshop with fusion because we also present at the American Physical Society meeting every year for the Teachers' Day. And so we have quite a few activities and videos and so forth built up for that. So we also have the history and fate of the universe, gravitation, and quantum information charts. Again, all available with resources and pictures of the chart on our website, but also available on Amazon if you want to buy a physical copy of them. So the particle charts started us out, and our charts have been seen on different things in the media, such as the Big Bang Theory, Donnie Darko, Hulk, 13 Conversations About One Thing. So they are used to sort of point out the
physics
science.
Buildings. You will find them in many physics buildings hallways.
And other places you can find CPEP on Twitter, Facebook, Pinterest, Instagram, LinkedIn, Amazon. As I mentioned, we have our charts available there. If you're interested in just some garb with this, TeePublic has masks, mugs, t-shirts, anything to, get the science out. And we just started with digital downloads on Etsy. If you just search contemporary physics, you should find those. So if there's a certain portion of the chart or a certain chart that you want to use, you can do a digital download there. Now, first of all, I've got a little question for everybody. So let's see if this works. In one word, what comes to mind when you hear the word fusion? If you can go to wooclap.com. And put in your answer for that. All right, so we have some great answers there. Fusion in stars, energy, merging, nuclear energy. Nice. All right, and what is your current comfort level with teaching plasma or fusion topics? All right, so good. We're in that range where we feel somewhat comfortable and maybe can get a couple other ideas today. So the fusion chart, as I showed you on the website, has different sections, and those various sections, I'll just point out a few things from each one. Katrina, feel free to add in here as we take a closer look at this. Oh, you know what? I wanted to go back to the website. Maybe go back to the website. No.
So if you guys manage to get to the website, there's on the page where it's fusion, it says a closer look. If you click on that, it takes you to the zoomed in parts of the chart. There it is.
Okay. So if we go to the closer look, one of the images that is on the chart is telling us about the temperature and how the temperature must be high in order to create fusion. And the particle density has to be high in order to do so. The solar fusion chain, and I'm going to share with you a pretty good video that describes the solar fusion chain in just a minute. Where the energy comes from and different sources that we have for energy. And the rate coefficient, or how quickly this fusion can take place, as a function of the temperature, and how the primary process in our sun, the proton-proton, is or differs from the deuterium-tritium reaction that we use on Earth. And the deuterium-tritium reaction, which I believe Katrina has on her shirt, and I also have on my shirt. This is one of the products available at TeePublic, and a small chart of the binding energy versus nuclear mass. So where we're more likely to get fusion to occur is those small nuclear mass particles. So back to the chart again. Can you see the what is fusion page? Yes, are we there?
Yes.
All right, thank
Yes.
you. Okay, so again, the process where two light atomic nuclei combine to form a heavier nucleus, releasing a large amount of energy, and it's the process that powers our sun. So that is that proton-proton fusion chain. Now, I will share the link for this video. It's not a CPEP video, but it does explain that proton-proton. It's 6 minutes long. I don't know that we really want to watch it all now, but it does. I'll just watch the first minute or so with you if you want to explain that to
The heat
students.
we feel from the sun is emitted from its surface, which is over 6,000 degrees Celsius. That's nowhere near hot enough for fusion to take place though. So let's move deep down into the core of the sun, where the temperature and pressure are high enough for fusion reactions to take place. At the sun's core is a dense hydrogen plasma, a soup of electrons and protons. The protons are shown here in red, and it's these particles that we'll focus on. They bounce.
All right, I'm going to go ahead and stop it there, but I will share the link to that before we leave, and put that in the chat. So one of the reasons, and one of the reasons that our workshop today is called plasma infusion, is because in order to create that possibility of fusion, we need to have materials in the plasma state, or the fourth state of matter. And it is when a gas is so highly energized that the electrons break free from the atoms and create a mix of charged ions and electrons. And those plasmas will conduct electricity well, and only in that ionized state can the plasma nuclei collide and fusion can occur. So again, a section of the fusion chart, fusion and plasmas chart, is that temperature versus number density, showing what some different types of plasmas are. And it's a good place to start with the kids, the students, to see if they know what some plasmas are that we encounter here on Earth, like flames, we see the aurora, and so on, fluorescent lights. And the particles that are low mass binding energy are those that can fuse. So binding energy is important, binding energy versus the nuclear mass, and particles that are in that small, again, nuclear mass are going to fuse, whereas if they're in the larger nuclear mass, they're going to be more susceptible to fission. The deuterium-tritium reaction is a reaction that can actually be more achievable here on Earth than the proton-proton. And we have a short activity that is a simulation of the deuterium-tritium that we'll show you in just a minute. So And again, we already saw these on the website, so I'm going to skip by some of these. So we're going to go through a few demo activities that can be used in your classroom. They're available on the website, cpepphysics.org, with demos on YouTube. And we're going to show the demos via the YouTube videos so that you can access them later. And any questions are welcome, certainly. We have a few of them listed down here, but we'll just go through them one.
Let me just interject. When Sherry says they're
Sure.
available on the website, she the teacher's handouts as well as the student handouts are there, so you can download those files.
And let's go ahead and go to that right now. Oh. All right, so if you go to Plasma Physics and Fusion and teacher resources, there are all of the activities on the teacher resource page, as well as teacher notes. And for example, if we want testing a physical model, which is one we're going to start out with, you can download this in PDF or in Word documents, so you can change whatever you want to about it, shorten it if you would like, and so on. So if you're interested in any of those activities, they are there on the website. And there's quite a few of them. We're not going to show all of them here, but we will show most of them. All right. And that is not the password. So I will share the password before we're done here too. All right.
And the password is to get to the teacher's notes. The student handouts you don't need the password for.
Good. Thank you, Katrina. All right. So the first one that we're going to show is simulating fusion, and it is a simulation of the deuterium and tritium reaction that occurs in fusion reactions here on Earth. And the activity uses just bottle tops with Velcro attached, which are placed in a box and then shaken. And some of the tops will fuse together. And this is used to show or demonstrate how time, particle density, and temperature affect the number of fusions produced in a hypothetical reactor. So we have a short video. If you see, we just have a box. You can change the size of the box to change the confinement size. And our bottle tops have Velcro on them, little circles of Velcro. And one of the sizes, perhaps the deuterium might have the rougher Velcro, and the tritium, the larger size, would have the softer Velcro on them. And I'll show you a small
So here we have the setup for simulating fusion, testing a physical model. This simulation uses bottle tops with Velcro attached that are placed in a box, which is then shaken. Some of the tops will fuse together, and this is used to demonstrate how time, particle density, and temperature affect the number of fusions produced in a hypothetical reactor. The emphasis is on producing a physical model from thinking about a hands-on simulation. So Jenna is going to do this experiment with us. And the first thing she's going to do is take the bottle caps that are in the bags There are 10 of each, so she's going to start out with that, place them in the box. And she just started her metronome because she's going to keep this at the same pace. What we're going to vary this time is the time. So she's first going to
Did we lose the sound?
do
There we go.
5 seconds of shaking.
Have one.
One fusion, okay? All right. After breaking that apart, she is going to try with 10 seconds.
Okay, so I assume you get the idea there in changing the time. There's also varying the particle density. And in that video, she will then change the different or the number of particles in her different trials. And then there's varying the temperature. And the varying the temperature is varying the kinetic energy of the molecules or of the particles. And so the different speed that she's
So
shaking
the
them
last
at.
thing that can be changed is the particle energy or the temperature. And that can be shown by changing how vigorously the box is shaken. So it can be shaken at a steady, slow pace, or that rate can be increased. And
Again, I think you get the idea on that, but you know, we can have graphs made in the activity. There is the option to do graphs and some graphing activities, or just go qualitative. Katrina, anything to add to that one?
It gets loud. The students can shake very vigorously and it can get very loud.
Yeah. They do seem to have a really good time with it. They get a little bit of the idea of the things that are variables in a fusion reaction and what kind of things in a tokamak or in any fusion reactor are problematic. You know, that the scientists have to make sure that they keep that temperature and they keep that particle density and they keep the time high enough. Any questions?
So the handout actually accompanies this, walks them through that, has them recording their data. And I believe there's graphing involved, isn't there, Sherry?
Yes.
Yes. Yeah.
Yeah. And the password, as I look this up here, I believe is, I was just looking to see how many things were capitalized, and it is CPEP Science is Cool. I'm going to put that in the chat. So science is capitalized, all of CPEP is capitalized, science is capitalized, is and cool, first letters of each. And that should work to get you into the teachers' activities of that as well.
in this simulation,
All right. Another thing that is pretty easily simulated is the analogy of nuclei repelling when they're far apart and attracting when they are closer. And of course, in the actual fusion reactions. They're repelling because of the electromagnetic repulsion or the electric repulsion, and they are coming together because of the strong nuclear force when they're close enough. But we can use the electromagnetic force to simulate that, and it's also a good way to talk about electromagnetic forces and magnets, if that is what you're covering in class. So, and this one I want to point out is the beginner version of this, and we'll show the slightly more involved version in a second.
This set of ring magnets with a little bit of Velcro on the insides and a pencil and eraser caps is the setup for modeling interactions in a nucleus. So strong magnets, or magnets with Velcro, can be seen to repel when far apart and attract when brought closer. This presents a kind of analogous situation to nuclei repelling when far apart and attracting to fuse when closer. This can also be used to explore the nature of induced magnetic moments. So Jenna is going to first try to push the two magnets closer together, and you can tell that when they get closer, they are pushing apart from each other. So the way that we will try to fuse them is to add energy to this situation. And to add energy, what could she do? Go ahead, Jenna, add some energy to it. And she added enough energy, they are now fused together. All right. So
All right, so that is the simple version, mainly either a starting point or for younger students. And then there's another activity called long-range repulsion, short-range attraction. And this one is honestly one of my favorites for doing with students when we're talking about electromagnetic fields and magnetism. But then you can pull in the idea that it's very similar to the difference between the electrostatic repulsion and the strong nuclear attraction.
one of the harder ideas to grasp in fusion is that nuclei which strongly repel at long range compared to the size of a nucleus can strongly attract at short range. This activity produces a magnetic example of repulsion switching to attraction as two objects get closer. It doesn't work the same way as forces between nuclei work, but it does provide a great analogy. So Jenna has two neodymium magnets, two small neodymium magnets, and she's going to place the like sides near each other, and she definitely notices a repulsion between those two sides. Now she'll take those and put them on opposite ends of a piece of rebar, and you notice attraction. So this can be explained through the activity and through magnetic forces. Now she's going to take those off of there, and still making sure that the like sides are facing each other, she's going to put one on one side of a ball bearing, and as she brings the other one near, she still notices repulsion, but if she shoves them close enough together, she's going to notice that there is attraction. Okay, taking those off, still making sure that there is a repulsion between like sides. She's going to put one on the side of a machine nut, and there's two machine nuts there, and when she brings it, you notice something strange appears, that we end up with the machine nuts splitting apart. So that is what the activity is going to explain and make the analogy to the nuclei.
Okay, so again, there is that long-range repulsion and short-range attraction. The activity and the teacher's notes, while we don't have a lot of time here to go through the ideas, the activity does very detailed go through what's going on, gives diagrams and so on of how the magnetic fields are induced in that. So just to give you an idea of what the activities look like, this is the student activity portion, and it's pretty step by step for the students. Okay, now give us a little bit of what you're thinking is going on. Let's try it this way. Tell us what you think is going on, and so on. And then if you go to the teacher's notes, they are fully explained so that you can give the students a little bit of background information with that. Now, there's also the physics of plasma globes, and plasma globes right now seem to be fairly inexpensive and on sale, I should say, at places like Walmart, for example. They are, I guess, trying to sell them to college students who are going off to school. So there are a couple sales here and there. But in this activity, the students develop a set of reference spectra using spectrum tubes, and then the spectral lines from the plasma globe are observed and compared with the results to see if they can figure out maybe what could be in that plasma globe.
So here we have the spectra of a plasma globe, and this is using a small diffraction grating and creating one streamer off of the top of the plasma.
Now, what you have to remember, though, is that there is a lot of energy there. So the fingers of whoever who's doing that are going to get toasty warm. But of course, they can take them off and restart again. So you can see the spectra that's there. And then the students can compare that to the spectrum of a hydrogen tube or krypton or neon and see if they can find similar lines. And of course, you can get more quantitative with this if you have a spectroscope and you can see at, what wavelength those lines are at. Katrina, anything to add to that? I'm trying not to take too long because, we said 45 minutes to an hour, but.
No, I can't think of anything.
Okay. Any questions? No? Okay. Okay. We also have an activity that's plasma globes and body capacitance. And the reason that we are pulling in capacitance into this is because the plasma globe acts somewhat like a capacitor. With the glass portion on the outside, the charges aren't going through the glass, but the charges that are interior to the plasma globe are actually pushing charges away on the exterior. And so very similar to one side of a capacitor and then the dielectric, and then the other side of the capacitor. And this is a very simple capacitor. It does not hold a charge, which is actually much safer to use with the students because they're not going to walk up to it 5 minutes later and actually be shocked. But it is simply a cutout piece of cardboard with aluminum foil on it, cutout piece of cardboard over here in a circle with aluminum foil, a little cardboard box cut out to hold the pieces at a certain distance. And each one of these thin pieces of cardboard has a thumbtack through it just to give a point of contact, as you'll see in the video.
So we have a homemade capacitor.
Now, I always use the Odin or Tesla coil, and don't let the students use it, but I would assume if you're, I don't know, do you let the students use it in college, Katrina?
No.
No. Okay. All right. But it is a good demo. So
And I'm going to bring the Tesla coil to one side or one place on the left side. You'll notice that.
So I know that it's hard to hear on this one because of the noise from the Tesla coil. But when you bring it to this side, if you notice, there's a spark over here and it's building up a charge on this plate, which is pushing away the electrons on this plate, and you can see the spark right over here, but there's not a spark interior to that. So the charges aren't jumping, it's just that that electric field from these is pushing away the charges on the opposite side. Occasionally there is a spark that jumps, and it's a good place to talk about capacitor breakdown and what goes on in that situation.
The electrons from the Tesla coil push the electrons away.
And in the plasma globe, the same situation is happening. You know, students will think, oh, I'm going to get shocked by touching the outside of the plasma globe, and that's not what's going on. The glass is an insulator, and it's keeping those charges from jumping across.
So we have
you can see that if
So in this demonstration, we have a small piece of aluminum foil sitting on top of the plasma globe, and then we have a probe that is attached to the ground plug of our voltage supply, so it is grounded. And when Jenna brings the probe very close to the aluminum foil, you can see a spark, and that's evidence of the electric field that is emanating beyond the glass.
So you can see that there's a spark between these sides, just like it was with the capacitor.
So in this
And again, this is another one of my favorite ones to use with the kids when we're talking about electric fields in AP Physics. The activity, again, is online, but you can use a multimeter, plasma globe, and as the video will show, we have a probe that's on a stick or a meter stick. And at different distances, you're going to see a different voltage reading on the multimeter.
If you have a digital multimeter with an AC volt setting or an oscilloscope, you can do a rough quantitative test of electric field strength in relationship to distance and direction from the globe. In this situation, Jenna is holding the probe next to the plasma globe, and you can see on the oscilloscope our readings of around 600 to 610 volts. Now she's going to move it carefully and slowly away, and you can see the readings drop. If you have a digital
And again, this can be more qualitative or quantitative. It can take 5 minutes if you want to use it as a demo, or you can have the students graph the distance and the voltage and see the relationship there. And it does turn out to give pretty good graphs. So in the PowerPoint, and if you're interested in the PowerPoint, I can share it through a shared Google Drive. But I have some links to the diffraction gratings, the plasma globes. Do not get the battery-powered plasma globes. I would definitely suggest against that. You can get them very cheaply, but they deplete the batteries so quickly that it's, it's sort of like when you buy your printer and then you end up spending all the money on the ink. You can buy the cheap plasma globe and then you end up spending all the money on the batteries. Some websites I would suggest, PPPL is Princeton Plasma Physics Labs. Eater.org gives a lot of information about the fusion process and tokamaks and creating energy. And then, of course, cpepphysics.org. And if you just go to YouTube and you look up CPEP Physics, you can find our videos there. And the video, the nuclear fusion in the sun that I suggested before, is written down here.